Everything you see may be a tiny fragment of reality. The universe appears vast, but it might be constructed on hidden blueprints we are only starting to read. This journey will explore 30 incredible theories about the secret architecture of everything, from vibrating cosmic strings to holographic projections and realities within black holes. By the end, you will see the cosmos not as a random void, but as a carefully structured masterpiece with layers we are just beginning to peel back. What if the Big Bang was not the beginning, but a collision in a higher dimension? Could our entire existence be a shadow cast from the edge of space? We are about to dive into the most thrilling ideas in modern physics. Which cosmic secret feels the most real to you? These hidden blueprints might be written in threads thinner than a single atom. Our first theory proposes that the universe is woven with cosmic strings, unimaginably dense cracks frozen into the fabric of space-time from its very first moments. Picture the universe cooling from an unimaginably hot, dense state like water freezing into ice. As it cooled, the very fields that govern reality might have undergone a phase transition, and just as ice forms cracks, space-time itself could have fractured. These fractures are cosmic strings, not made of matter but pure, twisted energy. They are theoretical one-dimensional flaws, thinner than a proton, yet they could stretch across the entire cosmos from one galaxy cluster to another. Their properties defy common sense. A single cosmic string, though unimaginably thin, would be so dense that a mile of it might outweigh an entire mountain. This incredible mass warps spacetime around it with ferocious gravity. This gravitational distortion is so extreme it could act as a lens, bending light from distant stars and galaxies. Astronomers might one day spot a strange, perfectly doubled image of a galaxy, a cosmic mirage with no visible cause, and that could be the signature of a string slicing through our line of sight. The strings are not static either. They are thought to vibrate and oscillate, and when they snap or intersect, they could send powerful ripples through spacetime itself, gravitational waves with a unique, sharp signature unlike those from black hole mergers. Finding one would be a direct window into the universe's first fraction of a second, a fossil from the era of grand unification when all forces were one. It would confirm that the cosmos underwent dramatic, violent phase changes as it expanded and cooled, leaving permanent scars in its structure. Their detection, perhaps through a telltale pattern in the ancient cosmic microwave background or a burst of gravitational waves, would do more than add a new object to the cosmic zoo. It would prove that the large-scale architecture of everything is built upon defects and imperfections, a tapestry with flaws woven into its very foundation. That cosmic tapestry may be far simpler than it appears. The second theory proposes a truly radical idea, the holographic principle. It suggests that all the information describing everything inside a region of space, every star, every planet, and every thought in your head, could be perfectly encoded on its two-dimensional boundary, like a cosmic movie screen. Think of a three-dimensional movie you watch at the cinema. The thrilling depth and movement you experience is not actually happening in the room. It is all projected from a flat, two-dimensional strip of film. The holographic principle applies this same logic to the universe itself. Our rich, three-dimensional reality, with all its volume and depth, might be a magnificent illusion, a projection from a vast, two-dimensional surface at the very edge of everything we can see. This astonishing idea did not come from nowhere. Its roots lie in the strange physics of black holes. When matter falls into a black hole, it seems to vanish forever, taking all its information with it. This violates a fundamental rule of quantum mechanics, which states that information can never be truly destroyed. This is the famous black hole information paradox. Physicists wrestling with this problem made a startling discovery. They found that the maximum amount of information a region of space can hold is not proportional to its volume, but to the area of its surface. It is as if the entire interior of a sphere is described by pixels painted on its skin. This led theorists, particularly in string theory, to a profound suspicion. Perhaps the three-dimensional world we experience is not the fundamental reality. Perhaps the true, fundamental degrees of freedom, the real code of the cosmos, live on a distant, two-dimensional surface. Our reality is then a holographic projection of that data, a cosmic rendering so perfect we cannot tell the difference. If true, this would solve the information paradox. The data of what falls into a black hole would not be lost inside it, but would be smeared and preserved on its event horizon, its two-dimensional surface like intricate engravings on a cosmic tombstone. The implications shake our understanding of existence. Space and time themselves may not be fundamental building blocks, but emergent properties that arise from this vast, complex information processing happening at the boundary of reality. We are living inside a simulation, but not one made by machines. It is a natural hologram projected from the edge of space. Yet if our reality is a hologram, where is the projector? The answer might lie in a cosmos so vast it contains everything, everywhere, all at once. This brings us to the third theory, the first level of the multiverse. It begins with a simple, almost humble scientific observation. Our best measurements suggest the universe is flat, and crucially, it appears to be infinite. If space truly has no end, and if the matter within it is spread roughly uniformly as our telescopes indicate, then a staggering mathematical truth emerges. In an infinite space with a finite number of ways to arrange particles, every possible configuration must repeat, not just once but an infinite number of times. Think of it like rolling a set of cosmic dice forever. Given enough throws, you will eventually roll the exact same sequence of numbers, now scale that up to the entire universe. Somewhere, impossibly far beyond our observable horizon, there exists a region of space where the particles are arranged exactly as they are here in our solar system. That means there is another Earth, another you, reading or listening to something just like this, but the dice rolls do not stop there. In other distant realms, the configurations differ by just one particle. In those realities, you might have chosen a different path this morning, or the outcome of a historical event shifted by a single vote. Further out still, the variations become wilder, with planets that never formed or laws of physics that took a subtly different shape. This infinite tapestry is not science fiction, but a direct consequence of our leading model of the early universe, cosmic inflation. This theory posits that a fraction of a second after the Big Bang, space itself expanded faster than light, stretching a tiny, uniform patch into the vast, flat cosmos we see today. If that inflationary process never stopped, as some models suggest, then it created an endless, ever-growing expanse of space, a level 1 multiverse. The scientific basis is rooted in cosmology and probability, yet it launches profound philosophical puzzles. If infinite copies of you exist, what does that mean for your identity, for your choices? Is every decision you make simply selecting which version of you to become, while other versions live out the alternatives? And if every possible event occurs somewhere, then the very concept of everything takes on a dizzying new scale. It suggests that the hidden structure of reality is not a single, unique blueprint, but an infinite library containing every story that can possibly be written, with our lives merely occupying one of its endless, identical pages. But an infinite cosmos of identical copies is only the first layer of strangeness. To find truly alien realities, we must look beyond our own bubble of spacetime. The fourth theory introduces the level 2 multiverse, a vision born from the most successful idea in modern cosmology, inflation. This theory suggests that the rapid expansion that shaped our early universe never truly stopped. Instead, it continues eternally, like a pot of water that never stops boiling. In this eternal inflation, the fabric of spacetime is a seething, frothing sea of energy. Every so often, in a random patch, the inflationary energy decays like a bubble forming in the boiling water. That bubble stops inflating and settles into a stable, expanding universe of its own. Our entire cosmos, with all its hundreds of billions of galaxies, is just one of these bubbles in an endless, bubbling meta-universe, a cosmic foam where new universes are constantly being born. The critical difference from the Level 1 multiverse is that each of these bubble universes is not just a copy of our own with rearranged particles. They are fundamentally different realms. When a bubble nucleates, the decay of the inflationary field can settle into different stable states. This is like water freezing into ice, but with countless possible crystal structures. Each stable state corresponds to a different set of physical laws and constants. In one bubble, the strength of gravity might be 1,000 times stronger, causing stars to burn out in mere millions of years. In another, the nuclear forces might be too weak to allow atoms to form at all, leaving a universe of scattered particles. Some bubbles might have 4 dimensions of space, or 5, or only 2, realities where geometry itself is unrecognizable. This theory provides a powerful, if unsettling, answer to one of physics' greatest mysteries, the fine-tuning problem. Our universe's constants, like the strength of gravity or the mass of an electron, appear exquisitely balanced to allow for stars, planets, and life. Alter anyone by a tiny fraction, and complex structures could never form. The bubble universe theory suggests there is no deeper reason for this perfect balance. In the infinite froth of eternal inflation, every possible combination of constants exists in some bubble. We could not possibly find ourselves in a bubble where the constants do not allow for our existence. We are, by necessity, in a habitable bubble, marveling at the luck that seems too good to be true. It is not luck, it is a cosmic selection effect. We are the observers that the bubble produced. The silent, invisible expanse between these bubbles is a frontier beyond imagination, a meta-space where the rules of our physics do not apply, and where new worlds are forever budding into being, most of them barren and dark, but a rare few, like ours, glowing with the light of possibility. The bubbling foam of eternal inflation creates universes with different laws, but there is a theory that generates new realities without changing a single constant. It happens every moment right here. The fifth theory is the many worlds interpretation of quantum mechanics, a vision of reality where every possible outcome actually occurs. This is the Level 3 multiverse, and it does not require distant bubbles or infinite space. It unfolds within the quantum realm, with every decision, every quantum event forcing the cosmos to split. Think of the famous thought experiment, Schrödinger's cat. In the classic telling, the cat in the box is both alive and dead until someone looks, at which point the wave function collapses into one definite state. The many worlds interpretation rejects this collapse entirely. It says the cat is both alive and dead, but those two possibilities no longer coexist in a ghostly haze. Instead, the universe itself divides like a forking path in a cosmic forest. In one new, equally real branch of reality, the radioactive atom decayed, the poison was released, and the cat died. In the other new branch, the atom did not decay, and the cat lives on. Both outcomes are real, but they happen in parallel worlds that no longer interact. There is no single moment of observation that chooses one over the other. The split is a fundamental and continuous process woven into the fabric of quantum mechanics itself. This solves the deep unease of quantum weirdness. Particles can be in two places at once, not because they are fuzzy clouds of probability, but because each definite location exists in its own branching timeline. Every time an electron faces a choice, every time a photon could go left or right, the universe duplicates to accommodate all possibilities. The implications for our own lives are staggering. Every choice you make, from a major life decision to the random firing of a neuron, could be a point of branching. In one world, you turned left on your walk and had a pleasant day. In another, you turned right and met someone who changed your life. Both versions of you are equally real, living out the consequences in separate, non-communicating streams of reality. This challenges our deepest notions of identity and free will. Are you the product of a single chain of decisions, or is your consciousness somehow following just one thread in an infinite tapestry of all your possible selves? The scale is beyond human comprehension. Since the Big Bang, the number of quantum branching events is unimaginably vast, suggesting a multiverse of truly cosmic proportions, not spread out in space like the bubble universes, but layered atop each other in an ever-expanding tree of alternate histories. It proposes a cosmos of limitless potential, where every story that could be written is being lived moment by moment in a silent, branching symphony of realities. Branching worlds and bubbling universes still operate within a familiar framework of space, time, and physical law. But what if the ultimate hidden structure is not physical at all? The sixth theory proposes the most radical multiverse of all, the mathematical universe. This idea, championed by physicist Max Tegmark, suggests a breathtakingly simple yet profound principle. Every mathematically consistent structure is not just a description of a possible reality, it is a reality. Our universe is not merely described by the elegant equations of physics, it is those equations brought to life. In this view, mathematics is not a human invention, a language we created to map the world. It is the world itself, the fundamental substance from which all realities are woven. We are not writing the rules, we are discovering them, like explorers deciphering an ancient, eternal code. Consider the game of chess. Its rules form a perfectly self-consistent mathematical structure. There are pieces with defined movements, a grid of squares, and logical conditions for victory. According to the mathematical universe hypothesis, that structure does not just exist as an idea in our minds. Somewhere in the grand ensemble of all possible mathematical structures, the universe of chess exists as a physical reality. Not with little wooden pieces on a board, but as a space where the entities we call rooks and bishops obey those precise rules of motion and interaction. The same goes for any system you can define with perfect logical consistency, from the geometry of a four-dimensional cube to the intricate patterns of a never-ending fractal. Our own cosmos, with its three spatial dimensions, quantum fields, and general relativity, is simply one particularly rich and complex mathematical structure that contains self-aware substructures, us, who are perceiving it from within. The implication is staggering. It means that physicists are not inventors crafting models to approximate nature. They are archaeologists uncovering the timeless Platonic truths that constitute existence. When Einstein discovered the equations of general relativity, he was not imposing a new idea onto the universe, he was revealing its true mathematical identity. This solves the mystery of why mathematics is so unreasonably effective at describing the physical world. It is not a lucky coincidence, it is because the physical world is mathematics. The theory pushes the concept of a multiverse to its logical extreme. The Level 4 multiverse contains every possible universe that can be defined by a coherent set of mathematical rules. This includes all the bubble universes with different constants from eternal inflation, and all the branching worlds of the many worlds interpretation. They are all just subsets of the vast, infinite landscape of mathematical existence. In this view, the quest for a theory of everything is not the search for the single set of equations that govern our universe. It is the search for the particular mathematical structure that we happen to inhabit, distinguishing it from the countless other equally valid structures that exist out there in the ultimate library of reality. We are living proof that one of these structures is complex enough to contain consciousness, asking questions about its own nature, slowly reading the lines of the cosmic code that we are written in. But mathematics alone cannot tell us how these structures physically manifest. For that, we need a concrete framework, a blueprint for reality's fundamental building blocks. This brings us to the seventh theory, M theory, and its central actors, brains. For decades, physicists pursued string theory, the idea that the tiniest constituents of nature are not point-like particles, but vibrating loops of energy, strings. Different modes of vibration would produce every particle and force we know. Yet a problem emerged. There were not one, but 5 distinct and seemingly valid versions of string theory. It was as if 5 different, perfect blueprints were found for the same cathedral. The breakthrough came with the realization that these 5 theories were not rivals, but different faces of a single, deeper, and more mysterious structure, M theory. Think of it like this: you have 5 different, detailed maps of a continent. One shows mountains, another rivers, a third shows forests. They all look different, but they are all describing the same underlying landscape from different perspectives. M theory is that unified landscape. It is the leading candidate for a true theory of everything, a single mathematical framework that could describe all particles, all forces, and the very fabric of space-time itself. The most revolutionary ingredient M theory introduces is the concept of brains, short for membranes. In this view, strings are not the only game in town. Brains are multidimensional objects like vast, flexible sheets existing within a higher dimensional space called the bulk. They can have any number of spatial dimensions. A 1 brain is a string, a 2 brain is a membrane like a sheet of rubber, a 3 brain has 3 spatial dimensions, and here is the breathtaking part: our entire universe could be a 3 brain. Everything we see, every galaxy, every star, every one of us, might be confined to the 3-dimensional surface of this immense floating membrane, adrift in a hidden, higher dimensional reality. This idea transforms our origin story. The Big Bang, the fiery beginning of our cosmos, might not have been a singular point of infinite density. Instead, it could have been a cataclysmic collision between our brain and a parallel brain floating in the bulk. Imagine 2 enormous sheets of space-time drifting silently in a higher dimensional void. When they finally touched, the impact would have released an unimaginable torrent of energy, heating our brain and filling it with the particles that would become everything. This is the ekpyrotic or brain collision model of the universe, a cosmic reset born from contact. This framework also offers a stunning explanation for one of nature's great puzzles, the shocking weakness of gravity. Gravity is fantastically feeble compared to the other forces. A tiny refrigerator magnet can defy the gravitational pull of the entire Earth. Why, in the brain world picture, the other forces, like electromagnetism and the nuclear forces, are like glue. They are made of open strings whose ends are stuck to our brain, so they cannot leave. They are trapped here on our 3-dimensional slice, but gravity, which arises from closed loops of string, is different. These loops are not pinned down. They can drift off our brain and leak out into the extra dimensions of the bulk. Gravity feels weak to us not because it is inherently feeble, but because its influence is diluted, spreading out into hidden spatial directions we cannot perceive. We are only feeling a tiny fraction of its true strength, a faint shadow of a force that operates in a grander, higher dimensional arena. In this vision, the hidden structure of everything is a dynamic, multidimensional landscape where our home is just one vibrating membrane in a symphony of unseen dimensions, and the very laws we take for fundamental might be local bylaws specific to the particular brain we are stuck on. That collision of brains offers a radically different creation story, one where the cosmos is locked in an endless, rhythmic dance. The 8th theory, the ekpyrotic universe, proposes that our Big Bang was not a singular, mysterious beginning from nothing, but a dramatic rebirth. In this vision, our 3-dimensional brain universe exists alongside a parallel brain, separated by a tiny gap along a hidden, extra dimension. Picture 2 vast, flexible sheets of reality, floating almost parallel to each other in a higher dimensional space. They are not static, they are drawn together by an invisible force, perhaps a spring-like tension in the bulk dimension between them. Over eons, they drift closer and closer until finally they collide. That impact is not a destructive crash, but a creative one. The immense kinetic energy of the collision is converted into a searing heat that fills our brain, creating all the matter and radiation we see as the hot, dense state of our cosmic dawn. This is our Big Bang, an event with a clear physical cause in a higher dimensional reality. But the story does not end there. After the collision, the brains bounce apart, stretched and energized, beginning a long period of expansion and cooling that becomes the universe we recognize. Eventually, the force pulling them together draws them back for another collision, resetting the cosmic clock in a new cycle. This suggests a cosmos without a true beginning or end, an eternal, cyclical process of creation, expansion, cooling, and renewal. It directly challenges the dominant inflationary paradigm, which posits a single, rapid expansion from a singularity. The ekpyrotic model replaces that initial burst of hyper-expansion with a slower, more gentle smoothing period before the bang, driven by the brains moving toward each other. This difference leaves a distinct fingerprint on the fabric of space-time. One of the most exciting ways to test this idea lies in the primordial gravitational waves, the faint ripples from the universe's birth. Inflation predicts these waves should be relatively strong, leaving a specific swirling pattern in the cosmic microwave background radiation. The ekpyrotic collision, however, is a much tamer event in terms of energy scales. It predicts these primordial gravitational waves would be exceptionally weak, perhaps too faint for our current observatories to detect. Future space-based gravitational wave detectors, listening for the deepest hum of creation, could therefore tell us which story is true. A clear, strong signal would point to a violent inflationary beginning. Silence or an incredibly faint whisper could be the signature of a brain collision, evidence that our universe was born from a kiss between parallel worlds in a hidden dimension. This theory transforms our origin from a mysterious singularity into a potentially observable physical event in a grander cosmic arena, suggesting that the greatest explosion we know might just be a regular occurrence in an eternal cycle of cosmic rebirth. While brains collide in higher dimensions, another theory takes a radically different path. It asks not what floats in space, but what space itself is made of. The ninth theory, loop quantum gravity, is string theory's great rival in the quest to unify general relativity and quantum mechanics. Its ambition is breathtaking: to quantize the very fabric of spacetime to find its indivisible atoms. In our everyday experience, space seems smooth, continuous, and infinitely divisible. You can always imagine cutting a meter in half, then in half again, forever. Loop quantum gravity declares this an illusion. It proposes that space itself is not a smooth backdrop, but is woven from a network of finite, one-dimensional loops. Think of the fabric of reality not as a perfectly smooth sheet of glass, but as an intricate tapestry made of individual threads. These threads are not in space, they are space. Where they intersect and link together, they create the network's nodes, and each of these nodes represents the tiniest possible volume, a fundamental pixel of reality. There is a limit to how small things can get. You cannot cut space into pieces smaller than this fundamental volume, which is about 1 trillion times smaller than an atomic nucleus. It is as if the universe has a minimum resolution, a cosmic pixel size. This discrete, grainy nature of space has profound consequences for the history of everything. In Einstein's general relativity, if you rewind the expansion of the universe, you are forced back to a point of infinite density and curvature, the Big Bang singularity, where the laws of physics break down entirely. In loop quantum gravity, this rewind hits a wall, or rather, a spring. As space is compressed to near its minimum volume, the quantum nature of spacetime creates a tremendous repulsive force. Instead of collapsing into a meaningless point of infinite density, the universe reaches a maximum compression and then bounces back, expanding once again. This is the Big Bounce, a cosmic rebirth where our expanding universe could have been preceded by a previous contracting phase. Our Big Bang was not a beginning from nothing, but a turning point in an eternal cycle. This quantum resilience also tackles the other great singularity, the heart of a black hole. In classical physics, matter crushed at the center of a black hole also reaches infinite density. Loop quantum gravity suggests that inside every black hole, at the moment of maximum compression, that same quantum repulsion kicks in. The collapsing matter might not vanish into a paradox but could rebound, potentially giving birth to a new, expanding universe on the other side of the event horizon, a baby cosmos forever disconnected from our own. In this view, black holes are not ultimate endpoints, but could be portals to new beginnings, woven from the same resilient, loopy fabric that prevents reality from ever tearing completely apart. The loopy fabric of spacetime suggests a granular reality, but what are the actual building blocks? The 10th theory, causal dynamical triangulations, offers a strikingly visual answer. It constructs the entire universe from tiny geometric pieces like cosmic Lego. The approach begins with the simplest possible shapes, triangles in a two-dimensional model, and their three-dimensional cousins, tetrahedrons. These are not shapes in space, they are the fundamental atoms of space and time. The theory's magic lies in what it does with them. You start with a vast, chaotic soup of these geometric pieces, all jumbled together with no order. Then you introduce two simple rules. First, they must connect only along their faces, building a consistent network. Second, and most crucially, you impose causality, meaning each piece has a clear before and after, a direction in time. This rule prevents impossible scenarios like time travel loops from forming in the microscopic structure. Now you let the system evolve. Using powerful computers, physicists simulate how these trillions of tiny triangles or tetrahedrons can connect and disconnect, exploring every possible configuration. It is a process of pure geometry finding its own way. From this primordial chaos of shapes, something remarkable happens. Without being told to do so, the network self-organizes. The random connections smooth out, and a clear, stable, large-scale structure emerges from the din. That structure is our familiar four-dimensional spacetime, 3 dimensions of space and 1 of time. It is like watching a digital image resolve on a screen. Up close, you only see individual, blocky pixels, but step back, and those pixels blend seamlessly into a smooth, recognizable picture. In this theory, each triangle is a pixel of reality, and the smooth, continuous cosmos we experience is the collective image they create. This is more than a neat analogy, it is a prediction. The simulations show that if you try to build a universe without the rule of causality, you get a hopelessly crumpled mess, a fractal foam with no clear dimensionality. But with causality enforced, the geometry always settles into a four-dimensional shape at large scales. It tells us that the dimensionality of our universe, the fact that we experience precisely 3 spatial dimensions and 1 time dimension, may not be a fundamental input but a natural consequence, an emergent property that arises from the way the quantum building blocks of reality are allowed to connect. The cosmos is not born with 4 dimensions, it grows them, crystallizing from a deeper, more chaotic geometric dance. From cosmic geometry, we now turn to a question that redefines the nature of reality itself. The 11th theory is the simulation hypothesis, a provocative proposal that our universe, with all its galaxies, history, and conscious experience, is not base reality, but an elaborate simulation running on the unfathomable computer of a far more advanced civilization. The reasoning begins with a simple extrapolation of our own technological progress. In just a few decades, we have gone from blocky, pixelated video games to immersive virtual worlds with their own physics, ecosystems, and increasingly complex artificial intelligence. If this trajectory continues for 1,000 or 1,000,000 years, the simulated realities created by such a civilization would be indistinguishable from physical reality to the beings within them. Now, if such a civilization exists, and if it has any interest in running simulations, perhaps for scientific research, entertainment, or ancestral archaeology, then the number of simulated universes would vastly outnumber the one original base reality. Statistically, if there are billions of simulated worlds and only one original, the odds are overwhelming that we are in one of the simulations. Philosopher Nick Bostrom formalized this trilemma in a famous paper. He argued that at least one of three propositions must be true. 1. Almost all civilizations at our level go extinct before becoming technologically mature. 2. Almost all mature civilizations lose interest in creating such simulations. Or 3. We are almost certainly living in a computer simulation. If the first two are false, if civilizations survive and choose to run simulations, then the third becomes a near certainty. Intriguingly, some interpretations of quantum mechanics seem to whisper in support of this idea. The strange observer effect, where quantum particles seem to exist in a haze of probability until measured, has been likened to a rendering engine in a video game. In a complex simulation, processing power is precious. Why render every detail of a distant star in perfect high definition when no one is looking at it? The universe could operate on a need-to-know basis, calculating precise properties only when an observation forces it to, a cosmic optimization to save computational resources. This is not yet a testable scientific theory in the traditional sense, but some physicists argue it could leave detectable signatures. If our reality is built on a discrete lattice, like a cosmic pixel grid, there might be a fundamental resolution limit. We could search for anomalies in the behavior of ultra-high energy cosmic rays, which, if space is perfectly smooth, should travel unimpeded. But if space has a pixelated structure, these rays might occasionally stumble, their energy subtly scattered in ways that betray the underlying code. The simulation hypothesis blurs the line between science and philosophy, forcing us to confront profound questions. If this is a simulation, does it make our experiences, our loves, and our struggles any less real? For us, within the system, the reality is absolute. The theory ultimately challenges our anthropocentric view, suggesting that the architects of existence might not be gods or random chance, but programmers in a reality we can scarcely conceive, running an experiment of cosmic scope where we are both the subjects and the curious investigators, slowly uncovering the glitches in our own matrix. The simulation hypothesis asks if we live in a crafted reality, but another theory suggests we might inhabit a natural cosmic tomb that is also a cradle. The 12th theory, the black hole universe, proposes that our entire cosmos, from the smallest particle to the farthest galaxy, exists inside a black hole belonging to a vast parent universe. This idea emerges from a fascinating mathematical mirror. When you look at the equations describing the gravitational collapse of matter into a black hole, and you reverse the direction of time, those same equations begin to look remarkably like the expansion of a universe from a hot, dense state. It is as if the physics of a singularity, the point of infinite density at a black hole's heart, and the physics of the Big Bang are two sides of the same coin. In this view, our Big Bang was not a unique event in absolute nothingness. It was the moment when a massive star, or perhaps an even more exotic object in a parent cosmos, collapsed catastrophically. As it crossed its own event horizon and plunged toward a singularity from our perspective inside that falling matter, the collapse would appear as a rapid, explosive expansion. We are not falling into a black hole, we are the product of its formation, living in the expanding fireball of its birth. This provides a startlingly elegant explanation for the origin of everything. The immense energy and density of the early universe simply reflect the extreme conditions of that initial gravitational collapse. Even the mysterious dark energy causing our universe to accelerate its expansion could be a subtle effect of our connection to the parent universe beyond our event horizon. The implications become a cosmic Russian doll. If our universe was born inside a black hole, then every black hole that forms within our own cosmos could follow the same script. When a massive star dies and forms a black hole here, the matter crushed at its core might not vanish into a paradox. Instead, the extreme warping of spacetime could trigger its own bounce or transformation, birthing a new, self-contained universe within, forever separated from our own by the one-way barrier of its event horizon. Each of those baby universes would have its own physical constants, perhaps slightly tweaked from ours, and within each, new stars would form, live, die, and create new black holes, each containing yet another universe. This creates a fractal, matryoshka doll structure of realities, an infinite regress of cosmos within cosmos. Our entire history, from the first stars to the rise of civilization, might be playing out in the interior of a black hole in another universe, and within the black holes speckling our own night sky. Entirely new cosmic stories are beginning, completely unknowable to us. We are both the offspring of a stellar collapse and the potential parents of countless new realities, living in a layer of existence where every dark pinpoint in the sky is not an end, but a sealed door to a beginning. But a cosmos born from a black hole still carries the memory of its violent origin. Another theory proposes a cycle so elegant it erases all traces of time itself. In Roger Penrose's conformal cyclic cosmology, our universe is not the first, nor will it be the last. It is simply one aeon in an endless, timeless sequence, where the death of one cosmos becomes the birth of the next in a perfectly seamless transition. This cycle hinges on a profound transformation that occurs in the far, far future, trillions upon trillions of years from now. The universe will have expanded to an almost unfathomable degree. All stars will have burned out, black holes will have evaporated through Hawking radiation, and even protons, the building blocks of atoms, may have decayed. What remains is a cold, dark, nearly empty expanse filled only with the faintest whisper of radiation and a sea of massless particles like photons and neutrinos. In this desolate state, something remarkable happens. According to Einstein's theory, mass and distance are what give the universe its sense of scale and time. But in this ultimate future, there is effectively no mass left, and distances have been stretched to such an extreme that the concept of size becomes meaningless. A universe that is essentially empty and infinite looks exactly the same as a universe that is a tiny, hot, dense point. It is a difficult concept to grasp, but mathematically, when you remove mass and scale, an infinite, cold emptiness can be perfectly reshaped or conformally transformed into a hot, dense singularity. Penrose proposes that the infinite future of our aeon can be mathematically remapped to become the Big Bang singularity of the next. It is not a bounce or a collision, but a smooth, continuous connection where the end seamlessly becomes the beginning. Time and scale dissolve, allowing the cycle to restart without a break. The most astonishing part of this theory is Penrose's claim that we might see evidence of a previous aeon imprinted on our own sky. He argues that when two supermassive black holes from the previous aeon collided in its final moments, the titanic burst of gravitational waves they produced would have left circular ripples in the fabric of spacetime. Those ripples, stretched across the transition into our new aeon, would manifest as faint, concentric rings of slightly different temperature in the cosmic microwave background, the afterglow of our own Big Bang. He and his colleagues analyzed data from satellites and reported finding exactly such patterns, concentric circles where the temperature variation was suspiciously smooth. This claim remains deeply controversial within the cosmology community, with many scientists arguing the patterns could be statistical flukes or artifacts of the analysis. Yet the idea itself is mesmerizing. It suggests that the universe is immortal, not in the persistence of matter, but in its endless capacity for reinvention. Every galaxy, every life form, every story is a temporary pattern in one eon, erased by the conformal transformation, only for new patterns to emerge in the next, in an eternal cycle without beginning or end. Our entire history is but a single chapter in a book with no first or last page, written in the fading heat of a fire that has burned forever. A universe that repeats forever still obeys a fundamental rule that no direction is special. Yet our most precise map of the infant cosmos hints this might be wrong. Theory 14 confronts the axis of evil, a name that perfectly captures its unsettling nature. This is not a structure in space, but a bizarre pattern etched into the cosmic microwave background, the faint afterglow of the Big Bang. When scientists created exquisitely detailed temperature maps from satellites like Planck, they expected to see a random, speckled distribution of hot and cold spots, like static on an old television screen. The universe should have no preferred direction, no up or down on the grandest scales, but the data revealed something deeply strange. The largest scale fluctuations, the biggest blobs of slightly warmer and cooler radiation, are not randomly oriented. They appear oddly aligned, their patterns whispering of a subtle axis that runs through the cosmos, and this axis seems to align improbably with the plane of our own solar system. It is as if the universe's grandest fingerprint has a curious tilt that points directly back at us. This alignment is cosmologically shocking. It violates the cornerstone of modern cosmology, the cosmological principle, which states that the universe is homogeneous and isotropic. In plain terms, it should look the same in every direction and have no center or special axis. The axis of evil suggests a preferred direction, a cosmic lopsidedness that makes our location seem strangely privileged, a modern echo of the pre-Copernican idea that we are at the center of everything. Explanations range from the mundane to the mind-bending. It could be a subtle, unaccounted-for artifact in the data processing, perhaps contamination from our own galaxy's dust or an instrumental quirk. Scientists have rigorously checked for these, and the stubborn signal persists. Other proposals are more radical. Perhaps it is a sign of the universe's topology, that space is not infinite but folded in on itself in a complex shape, like a video game screen where going off one edge brings you back to the other, creating repeating patterns that mimic an axis. The most profound possibility is that this alignment is not from our universe at all, but a fossil imprint from a time before the Big Bang. In theories like conformal cyclic cosmology, the collision of supermassive black holes in a prior eon could leave concentric ripples. In other models, the violent dynamics of the universe's birth might have stretched primordial irregularities into a preferred plane. If real, the axis of evil is a crack in our foundational assumptions, a whisper that the cosmos might have a grain to it like wood, and we are somehow aligned with its hidden structure. It is a mystery that makes our home feel, once again, peculiarly central to the story of everything. This strange axis might be a clue that space itself is folded in a way we cannot directly see. The 15th theory, cosmic topology, asks a deceptively simple question. What is the actual shape of space? We measure the universe to be geometrically flat, which suggests it could be infinite, like an endless sheet of paper. But a flat geometry does not necessarily mean infinite size. Space could be flat and finite if it is connected in a loop. Think of a classic video game world like the original Pac-Man screen. When your character moves off the right edge, it instantly reappears on the left. The screen is finite, but it has no boundary, no edge you can fall off. The topology, the way it is connected, creates a seamless, closed loop. Our three-dimensional universe could be wrapped in a similar but far more complex way. One of the leading candidates is called the three torus. Imagine a room where every wall is a doorway. If you walk straight ahead through the north wall, you instantly re-enter the room from the south wall. If you jump through the ceiling, you come up through the floor. This is a three-dimensional torus, a cosmic donut shape. In such a universe, a powerful enough telescope pointed in one direction would not see an endless void. Eventually, the light from our own galaxy would have traveled all the way around the cosmos and come back to us from the opposite direction. We would see ghostly, duplicate images of the Milky Way and every other structure like reflections in a hall of mirrors. Another mesmerizing possibility is the Poincare dodecahedral space. Here, the universe is shaped like a soccer ball, but with 12 curved pentagonal faces. The geometry is so perfectly matched that if you travel out through one face, you return through the opposite face, but rotated, as if you have been turned around in a cosmic kaleidoscope. In this elegantly finite cosmos, the patterns of distant galaxies would repeat in a beautifully symmetrical way. The most promising place to hunt for this evidence is not in galaxies, but in the oldest light we can see, the cosmic microwave background. If the universe is finite and wrapped, then the hot and cold spots in that ancient radiation would also be forced to match up. Light from the Big Bang would have taken multiple paths to reach us, wrapping around the cosmos like strands on a globe. This would create identical circles, pairs of matching patterns on opposite sides of the sky. It would be a cosmic fingerprint proving we live in a connected, finite space. Teams of astronomers have scoured the data from satellites like Planck, using sophisticated algorithms to search for these telltale matching circles. So far, no definitive pair has been found, but the search continues. The implications are profound. A finite universe would mean that everything in all of history exists within a bounded volume, no matter how vast. Every story ever told, every star that ever shone, would be contained within a grand, repeating chamber of space and time, a cosmic snow globe from which nothing, not even light, can ever truly escape. Our cosmic address is not as fixed as the stars suggest. We are all, the Milky Way and every galaxy in our neighborhood, caught in a relentless river of motion, pulled toward a mysterious region of darkness called the Great Attractor. This is not a force from within our galaxy, but a vast, unseen gravitational anomaly located some 250 million light-years away in the direction of the constellations Centaurus and Norma. Its pull is immense, dragging our entire local group of galaxies, along with thousands of others, toward it at a staggering speed of over 14 million miles per hour. For decades, this was a profound cosmic mystery because the Great Attractor lies directly behind the plane of our own Milky Way, in a region astronomers call the Zone of Avoidance. Here, thick clouds of interstellar gas and dust block almost all visible light from beyond, creating a blind spot in our map of the universe. It was like trying to find the source of a powerful wind while standing in a dense, blinding fog. The discovery came not from seeing the attractor, but from feeling its pull. By meticulously mapping the motions of galaxies, scientists realized they were all streaming toward a single point hidden behind our galaxy's dusty disk. The initial thought was terrifying and thrilling, that a previously unknown supermassive structure, perhaps a colossal concentration of dark matter or an unimaginably large black hole, was lurking in the void, dictating the motion of our corner of the cosmos. Further investigation, using telescopes that can peer through the dust with radio and X-ray eyes, revealed a more complex but no less grand truth. The Great Attractor is likely not a single, monstrous object. Instead, it appears to be the gravitational heart of an immense confluence of mass, centered on the dense Norma cluster, a gathering of thousands of galaxies, all bound together by their mutual gravity. This cluster itself is just the brightest knot in an even vaster structure, the Laniakea supercluster. Laniakea, a Hawaiian word meaning immeasurable heaven, is our true cosmic continent. It is a filamentary web of over 100,000 galaxies, spanning 500 million light-years, all flowing toward the same gravitational basin, the same cosmic watershed. The Great Attractor is the deepest valley in that basin, the point toward which all this galactic river water is draining. This discovery fundamentally reshaped our map of the universe. We are not simply part of the Virgo supercluster as we once thought. We are a suburb of Laniakea, and our Milky Way is a leaf caught in a slow-motion cascade down a slope defined by the invisible scaffolding of dark matter, toward a destination we now understand not as a monster in the dark, but as the center of gravity for our home supercluster. The mystery transformed into a revelation of our place in an immense flowing architecture, reminding us that even the grand motion of galaxies is just part of a larger gravitational dance. The Great Attractor pulls our local galaxies, but something even more immense may be tugging on the entire observable universe. Theory 17 confronts the phenomenon known as dark flow, a mysterious, coherent drift of galaxy clusters on the very edge of everything we can see. It is as if the cosmos itself is caught in a silent, universal current. This discovery came from a meticulous study of the motions of massive clusters, each containing thousands of galaxies. Scientists track them not by starlight, but by observing a subtle distortion in the cosmic microwave background, the oldest light in existence. This technique, called the kinetic Sunyaev-Zeldovich effect, works by measuring how the hot gas in these colossal clusters scatters the ancient photons as the clusters move. The results were staggering. These clusters, scattered across billions of light years, are not moving randomly. They show a coordinated streaming motion, all flowing in the same general direction, at speeds of nearly 2 million miles per hour. This is not the local pull of the Great Attractor or the expansion of space. This is a bulk flow on a scale that defies explanation by any known structure within our observable universe. The gravitational pull required to create such a vast, coherent motion would have to come from an accumulation of matter so enormous it lies beyond our cosmic horizon, in a realm of space whose light has not had time to reach us since the Big Bang. The implications are radical. One possibility is that during the inflationary period, when our universe expanded faster than light, it was not perfectly smooth. It may have been unevenly tugged or gravitationally influenced by another universe, a separate bubble of reality drifting close by in the multiversal foam. That external gravitational pull, imprinted during our universe's birth, would have set everything in motion on a universal scale, a fossilized current from a time before time. Another, even more mind-bending explanation is that there exists a structure of truly unimaginable scale, a super-duper cluster of galaxies or a vast concentration of dark matter so colossal it makes Laniakea look like a pebble. This titan would reside in the unobservable universe, its gravity reaching across the void to steer the visible cosmos like a distant magnet guiding iron filings. Dark flow remains a subject of intense debate, with some analyses questioning the statistical significance of the signal. Yet if it is real, it is our first potential evidence of something beyond the cosmic horizon. It suggests our universe is not an island, but may be part of a grander archipelago, forever drifting in a sea of darkness toward a source we can never see, guided by a hand we can only feel by its relentless universal pull. But a universe adrift in a dark flow raises an unsettling question about our own place within it. Are we truly the product of 13.8 billion years of cosmic evolution, or could we be a fleeting, random accident? The 18th theory, the Boltzmann brain paradox, confronts this terrifying possibility. It emerges from the deep laws of thermodynamics which govern the flow of energy and disorder. The second law states that entropy or disorder always increases in a closed system. A cup of hot coffee left alone will cool to room temperature, its heat dissipating into the air, a transition from an ordered, hot state to a disordered, uniform one. But thermodynamics is a statistical law. It is not impossible for all those scattered air molecules to randomly, simultaneously bounce back into the coffee cup, reheating it. It is just so fantastically, mind-bogglingly improbable that you will never see it happen. Now, extend this logic to an infinite or eternal universe. Given enough time and space, every possible arrangement of particles, no matter how ordered, must occur by random chance. This includes the spontaneous assembly of a fully formed, conscious human brain, complete with false memories of an entire life and a coherent universe. According to this paradox, in the vastness of eternity, it is statistically more likely for a single, disembodied brain to pop into existence for a split second, hallucinating the entire history of the cosmos, than for that entire ordered cosmos to actually evolve naturally. You reading this with all your memories and perceptions would be that brain, a momentary fluctuation in the void, experiencing a phantom reality before dissolving back into chaos. The paradox gets its bite when we compare probabilities. The universe we observe is incredibly low entropy, meaning it started in a highly ordered, dense state and has been unraveling ever since. The odds of our entire complex, structured cosmos arising from a random fluctuation are astronomically tiny. The odds of just one brain with a convincing illusion popping into existence, however, are still unimaginably small, but they are vastly, vastly greater than the odds of the real thing. This makes our existence, if the universe is infinite and eternal, seem absurdly, almost impossibly, improbable. Cosmologists do not actually believe we are Boltzmann brains, but they take the paradox deadly seriously. It acts as a razor, a tool to cut away theories of the universe that inevitably lead to this bizarre conclusion. Any cosmological model that predicts an eternal, endless future or an infinite spatial expanse essentially guarantees that Boltzmann brains will outnumber ordinary, evolved observers like us by an infinite factor. Therefore, a theory that makes our ordered history the most likely outcome is strongly preferred. This paradox pushes scientists toward models with a definite beginning and a finite future, or ones like cyclic cosmologies where low entropy conditions are naturally reset, making coherent, long-lived universes like ours not a statistical fluke but an expected feature. The Boltzmann brain is a ghost in the equations, a reminder that for our reality to be meaningful, the universe must have a structure that makes us not just possible but probable. The ghost of a Boltzmann brain is a statistical warning, but a different kind of ghost haunts particle physics. A crucial prediction from our most ambitious theories has never shown its face. Theory 19 centers on the magnetic monopole, a particle that should exist but stubbornly refuses to be found. You are familiar with magnets. Every bar magnet you have ever held has both a north and a south pole. Cut it in half and you do not get isolated poles, you simply get two smaller magnets, each with its own north and south. This seems to be a fundamental rule of nature, that magnetic poles always come in pairs. Yet our quest to unify the fundamental forces suggests this rule should have an exception. Grand unified theories, which attempt to merge the electromagnetic, weak, and strong nuclear forces into a single superforce, predict the existence of a particle with only one magnetic pole. This is the magnetic monopole, a particle that is just a north or just a south, a solitary point of pure magnetic charge. These would not be ordinary particles. They would be monstrously heavy, perhaps a quadrillion times more massive than a proton, relics forged in the searing heat of the universe's first fractions of a second when the forces were still unified. According to standard cosmology without inflation, as the universe cooled and underwent the phase transition that broke the grand unified force, defects in spacetime should have formed, much like cracks in ice. Magnetic monopoles would be one type of these topological defects, and they should have been produced in prodigious numbers. Calculations suggest they would be so plentiful that their immense mass would have dominated the density of the universe long ago, overwhelming everything else and causing it to collapse almost immediately. Our cosmos, filled with galaxies and life, simply could not exist if these monopoles were as common as the equations said they should be. Yet when physicists have looked, using everything from ancient minerals to massive particle detectors, they have found exactly zero confirmed monopoles. Their glaring absence is one of the most significant problems in cosmology. The solution, once again, points to cosmic inflation. The theory proposes that a tiny patch of the early universe, which may have contained a dense soup of monopoles, underwent a period of hyper-fast expansion. This expansion did not create new monopoles, it simply stretched the existing spacetime so unimaginably that the density of any pre-existing monopoles was diluted to virtually nothing. Imagine a single grain of sand in a small box. Now inflate that box to the size of the observable universe. The grain of sand is still there, but the chances of you ever finding it are essentially zero. Inflation spreads the monopoles so thin that our entire visible cosmos likely contains not a single one. Therefore, the fact that we do not see magnetic monopoles is not a failure of our theories but a stunning success. Their absence is a key piece of evidence supporting the inflationary paradigm. It tells us that something dramatic happened in that first sliver of a second, an event so powerful it wiped the cosmic slate clean of these monstrous relics, allowing the lighter, familiar particles to shape a universe that could last billions of years and give rise to us. The missing monopole is a silent witness to physics at energies we can barely conceive, its very non-existence speaking volumes about the hidden structure of reality. The missing monopole points to a universe fine-tuned for existence, yet another number in our equations defies all sense of tuning. The cosmological constant problem is not just a puzzle, it is arguably the most embarrassing failure of modern physics. It is the staggering disconnect between what our best theories predict about the energy of empty space and what we actually see. According to quantum field theory, the vacuum of space is not truly empty. It is a seething, bubbling foam of virtual particles that constantly wink in and out of existence. This quantum jitter should imbue every cubic centimeter of the universe with a colossal amount of energy, a vacuum energy so powerful it should act as a repulsive force of unbelievable strength. When physicists calculate this number, the result is not just a little off. It is wrong by a factor of 1 followed by 120 zeros. That is 10 to the power of 120. To grasp this scale, imagine the difference between the energy contained in a single proton and the energy contained in the entire observable universe. That difference is about 10 to the power of 40. The error in our vacuum energy prediction is a factor that is 10 to the power of 80 times larger than that already unimaginable gap. It is the worst prediction in the history of science. If the vacuum energy were anywhere near the theoretical prediction, the repulsive force would have been so immense, so instantaneous, that any matter trying to clump together after the Big Bang would have been violently ripped apart. Atoms could never have formed, let alone stars, planets, or life. The universe would have blown itself to pieces in a fraction of a second, yet we observe something entirely different. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating, driven by a mysterious repulsive force we now call dark energy. The strength of this dark energy, measured from distant supernova and the cosmic microwave background, is incredibly small, a gentle nudge that only dominates the cosmos after billions of years of expansion. It is real, but it is fantastically weaker than the quantum theory says it should be. So why is the number we measure 120 orders of magnitude smaller than the one we calculate? This is the cosmological constant problem, and it suggests a profound gap in our understanding. One proposed solution retreats to the multiverse. In a landscape of infinite bubble universes, each with randomly determined physical constants, the value of the vacuum energy would vary wildly. In almost all bubbles, it would be enormous, leading to instant cosmic disintegration. But in a vanishingly rare few, by pure chance, it would be tiny, just like ours. We, of course, can only exist in such a rare, stable bubble. This anthropic reasoning says the constant is not fine-tuned by law, but by the sheer statistical necessity of our existence. Another idea is that dark energy is not a constant at all. Perhaps it is a dynamic field nicknamed quintessence that evolves over time. Like a scalar field slowly rolling down a potential hill, its energy density could have started high in the early universe but decayed to the small value we see today. This would mean the acceleration we observe is a temporary phase in a much longer cosmic story. The most radical possibility is that we are fundamentally wrong. Our understanding of how quantum mechanics and gravity interact at the vacuum level may be deeply flawed. Perhaps there is a subtle cancellation mechanism we have not yet discovered, or gravity behaves differently on the largest scales, making the vacuum energy effectively zero. Each path forward carries immense weight, for solving this problem would not just fix a number, it would reveal whether the fabric of space itself is static or alive, random or inevitable, and whether our gentle, accelerating cosmos is a miraculous accident or the only possible outcome for creatures who ask such questions. A universe whose vacuum energy is 120 orders of magnitude off might need a more elegant symmetry to hold it together. Theory 21 offers just such a beautiful mathematical framework, supersymmetry. It proposes a profound and elegant extension to our current catalogue of particles, the Standard Model. For every known particle of matter and force, there exists a hidden, massive twin, a superpartner. Electrons would be paired with selectrons, quarks with squarks, photons with photinos, and the Higgs boson with a Higgsino. This doubling of the cosmic cast is not just for show, it solves several of the deepest puzzles in physics at once. First, it brings the fundamental forces closer to a grand unification. In our current equations, the strength of the strong, weak, and electromagnetic forces converge at extremely high energies, but they do not quite meet at a single point. The introduction of superpartners tweaks the math just enough to make all three lines intersect perfectly, suggesting they were truly one force in the early universe. Second, supersymmetry provides a perfect natural candidate for dark matter. The lightest of these superpartners, often called the neutralino, would be stable, electrically neutral, and interact only weakly with ordinary matter, exactly the properties required for the invisible cosmic glue holding galaxies together. It would have been produced copiously in the Big Bang and simply lingered, forming the gravitational scaffolding of the cosmos. Third, and perhaps most critically, it solves the infamous hierarchy problem related to the Higgs boson. The Higgs mass is extraordinarily sensitive to quantum corrections from other particles, which should drive its value to an astronomically high scale, making our universe impossible. But in supersymmetry, for every particle that pushes the Higgs mass up, its superpartner pushes it down by an equal amount. They cancel each other out with perfect protective symmetry, naturally explaining why the Higgs and by extension all particle masses are so small and stable. This elegant cancellation is like having two perfectly balanced teams in a tug of war, keeping the rope, the Higgs mass, firmly anchored at the center. Despite its mathematical beauty and explanatory power, supersymmetry faces a stark reality. The Large Hadron Collider, our most powerful microscope into the subatomic world, has so far found no direct evidence for any superpartners. These particles, if they exist, must be far heavier than many physicists had hoped, placing them beyond the current energy reach of our colliders. This lack of discovery has put the simplest, most elegant versions of the theory under immense pressure. Yet, supersymmetry is not fully ruled out. It could simply be that nature chose a more complex, broken version where the superpartners are just too massive for our present machines to create. The theory remains deeply woven into the fabric of our most ambitious frameworks, most notably string theory, which requires supersymmetry for its mathematical consistency. Without it, string theory loses its elegant stability. So the search continues, a hunt not just for new particles, but for the hidden symmetry that could complete our picture of reality, a whisper of balance in a universe that seems so desperately in need of it. Supersymmetry offers one elegant solution, but the problem it addresses is so extreme it defies belief. Gravity is not just a little weaker than the other forces, it is almost laughably feeble. The electromagnetic force that holds atoms together is stronger by a factor of 1 followed by 36 zeros. To grasp this staggering difference, picture the size of a single atom, a tiny cloud of electrons around a nucleus. Now picture the entire solar system, from the sun out to the distant comets. The gap between the strength of gravity and the strength of electromagnetism is that vast. A tiny refrigerator magnet can lift a paperclip, effortlessly overcoming the gravitational pull of the entire planet Earth beneath it. This is the hierarchy problem, and it is not just a curiosity. It is a screaming clue that our understanding of particle physics is profoundly incomplete. The problem centers on two fundamental energy scales in nature. The first is the electroweak scale, the energy at which the electromagnetic and weak nuclear forces unify, around 246 gigaelectronvolts. This is the realm of the Higgs boson and the masses of known particles. The second is the Planck scale, the energy at which gravity becomes as strong as the other forces, where quantum effects of spacetime itself dominate. That energy is a quadrillion times higher. Our universe seems to choose to live in a very specific, very low energy valley, and the question is why? Why is the Higgs mass, and therefore the mass of everything, so incredibly small compared to the Planck scale? In quantum field theory, the mass of the Higgs should be violently sensitive to every particle that interacts with it, receiving enormous quantum corrections that should naturally drive its value up to the Planck scale. This would make particles impossibly heavy and atoms could never form. Something must be protecting the Higgs, keeping it light. Supersymmetry, as we saw, proposes a perfect symmetry where every particle has a partner that cancels out these corrections. But there is another, equally thrilling possibility tied to the very shape of reality. If gravity is free to leak into extraspatial dimensions, as some brain world models suggest, then its true fundamental strength could be much, much higher. It only appears weak to us because its influence is diluted, spread out across hidden dimensions we cannot perceive. In this view, the hierarchy is not a problem to be solved by delicate cancellations, but an illusion created by the geometry of the cosmos. The immense gap between the two scales is then a direct measurement of the size of those extra dimensions. Either way, the incredible feebleness of gravity is not an accident. It is a signpost pointing toward a deeper layer of physics where forces are united, dimensions are curled, and the true strength of nature is hidden in a structure far grander than the one we perceive. The delicate balance protecting our universe from collapsing into chaos rests on a single, fragile field. The Higgs field permeates all of space, giving particles their mass and making the stable structures of matter possible. But what if this field, the very bedrock of reality, is sitting on a precarious ledge? Theory 23, the vacuum metastability event, proposes exactly that. It suggests our universe exists in a state of false vacuum. Imagine a ball resting in a small dip on the side of a vast, steep hill. That dip is not the absolute bottom of the landscape, it is a local valley. The ball is stable for now, but with a sufficiently powerful nudge, it could roll out of the dip and tumble all the way down to the true bottom far below. In this analogy, the ball is the value of the Higgs field. The local dip is our current vacuum state, and the true bottom is a lower energy state we have not yet reached. Our entire cosmos, with its specific laws and constants, is defined by the shape of this local dip. The terrifying possibility is that through a rare quantum fluctuation, a process called quantum tunneling, the Higgs field in a tiny region of space could spontaneously jump out of our dip. It would tunnel through the energy barrier and into the deeper valley. This would create a microscopic bubble of true vacuum where the laws of physics are completely different. In this new state, the Higgs field settles at a different value, which would very likely change the masses of fundamental particles, possibly dissolving atoms, dismantling nuclei, and rewriting chemistry itself. The moment this bubble forms, the rules change. The energy difference between the false vacuum outside and the true vacuum inside creates an immense pressure on the bubble wall. This wall would then expand in all directions at the speed of light. Nothing can outrun it. As it expands, it converts the space it touches into the new, true vacuum state. Every star, every planet, every memory would be erased not by destruction in a conventional sense, but by transformation. The universe ahead of the bubble would simply cease to exist as we know it, replaced by a new reality with alien physics where life as we understand it is almost certainly impossible. The calculations based on our current measurements of the Higgs boson mass and other parameters suggest that our vacuum is indeed metastable, not absolutely stable. This means such an event is physically possible, yet there is immense relief in the timescales involved. The probability of this quantum tunneling event happening in any given region of space is so infinitesimally small that the expected time for it to occur is many, many orders of magnitude longer than the current age of the universe. We are talking about timescales like 10 to the power of 100 years, a number so vast it has no meaning in human experience. For all practical purposes, our cosmic ledge is astronomically secure. The universe appears incredibly stable for the foreseeable future, a span that dwarfs the lifetime of stars and galaxies. So while the mathematics allows for this ultimate cosmic reset button, it is a speculative whisper from the far future, a reminder that the constants we rely on might be local and temporary bylaws in a much larger and potentially more unstable landscape of possibility. The stability of our cosmic laws may be a temporary blessing, but it raises a deeper question about our place in the grand design. If the universe is so vast and ancient, brimming with potential, why does it feel so profoundly empty and silent? This is the heart of the Fermi paradox, a contradiction that has haunted scientists for decades. Given the billions of stars in our galaxy, many older than the Sun, and the high probability of Earth-like planets, intelligent life should have arisen many times over. The galaxy should be teeming with civilizations, their signals crisscrossing the void, their artifacts perhaps visible in our skies. Yet when we listen, we hear nothing but cosmic static. The great silence is deafening. Where is everybody? One terrifying answer to this paradox imagines a hidden structure not of physics but of cosmic sociology. It is called the dark forest theory. Picture the universe not as a welcoming community, but as a vast pitch-black forest. Every civilization is a hunter, armed and terrified, hiding silently among the trees. They have learned a grim universal truth. Any civilization that reveals its location by broadcasting signals or expanding aggressively risks attracting the attention of others. And in a forest where you cannot know the intentions of another hunter, where technological advancement can happen in leaps, the only safe assumption is that any other civilization you encounter is a lethal threat. The safest strategy for survival is not to call out and make friends. It is to stay absolutely quiet, to hide and to listen. And if you do detect a rustle in the dark, the logical, coldly rational choice is to strike first with overwhelming force, to eliminate the potential threat before it can do the same to you. In this dark forest, broadcasting your existence is not an act of curiosity, it is suicide. This theory, powerfully explored in science fiction, imposes a hidden, grim rule on the architecture of intelligent life in the cosmos. It suggests that the great silence we observe is not an accident of rarity, but the result of a universal filter of fear. Every civilization that survives long enough to ponder the stars eventually learns this rule, either through bitter experience or cold logic, and chooses silence. Our own efforts, like the messages sent from the Arecibo telescope or the Voyager probes carrying golden records, could be seen not as hopeful greetings but as dangerous folly, like lighting a bonfire in that dark forest and shouting our coordinates. The dark forest offers a solution to the Fermi paradox that is both elegant and horrifying. It explains the silence not by saying life is impossibly rare, but by saying the survivors are impossibly quiet. The structure of the cosmos, in this view, includes not just the geometry of space and the laws of physics, but a ruthless ecological principle that governs the behavior of all advanced intelligence. The universe may be full of life, but it is a life that has learned to hold its breath, forever listening in the dark, afraid to make a sound. The silence of a dark forest suggests a universe indifferent to life, but what if the opposite is true? The 25th theory asks if the cosmos itself is structured to nurture existence. This is the Gaia hypothesis scaled to the universe. On Earth, the Gaia hypothesis, proposed by James Lovelock, suggests our planet functions like a single, self-regulating organism. Its biosphere, atmosphere, and geology interact in complex feedback loops to maintain conditions suitable for life, like a global thermostat. Extend that idea to the grandest stage. Could the universe possess its own subtle, self-regulating tendencies that favor the emergence of complexity and life? This is not about a conscious designer, but about the inherent properties of physical law and cosmic evolution that tilt the scales toward biospheres. The most compelling evidence for this cosmic bias is the shocking fine-tuning of the universe's constants. The strength of gravity, the mass of an electron, the energy in empty space, these numbers are not random. If any one of them were altered by even a minuscule fraction, the universe would be sterile. Stars would not form, atoms would not bond, and life would be impossible. It is as if the dials on the cosmic control panel were set with exquisite precision to allow for planets, chemistry, and ultimately, observers. This fine-tuning forces a profound question. Is it a staggering coincidence or a clue to a deeper principle? One answer is the anthropic principle, which simply states that we can only observe a universe capable of producing observers. In a vast multiverse where every possible set of constants exists, we naturally find ourselves in one of the rare habitable bubbles. There is no grand design, just statistical selection. We are the lucky winners of a cosmic lottery, but the cosmic Gaia idea pushes further. It wonders if, within our single universe, the laws of physics and the process of cosmic evolution are not neutral. Perhaps the emergence of life and intelligence is not a freak accident, but a natural, almost expected outcome of a universe whose architecture contains a bias toward complexity. Just as Earth systems seem to stabilize conditions for its biosphere, perhaps universal constants and the evolution of galaxies create a stable, long-lasting stage where the chemical building blocks of life are routinely forged and scattered. The formation of carbon in the hearts of stars, the delivery of water by comets, the relatively quiet galactic neighborhoods safe from constant supernova, all these could be seen as parts of a vast, slow-motion system that sets the table for life. It is a theory of a bio-friendly architecture where the hidden structure of physical law is not just a random set of rules, but a fertile ground from which consciousness can, and perhaps must, eventually sprout. This perspective does not require a guiding hand, but it does suggest a universe inherently pregnant with possibility, where life is not a lonely accident, but a natural expression of the cosmos becoming aware of itself. This cosmic bias toward complexity might hint at a universe that is not just structured, but actively thinking. Some of the most radical thinkers in physics are now proposing that the universe itself could be a kind of cosmic brain, a vast neural network in the process of learning its own laws. This is not a metaphor about consciousness, but a literal, mathematical proposal about the fabric of reality. In this digital physics framework, the fundamental building blocks are not tiny strings or loops, but simple computational units like neurons in a cosmic mind. These nodes connect and exchange information, and from their collective dynamic interactions, the phenomena we call particles, forces, and even space-time itself emerge. Imagine the pixels on your screen. Individually, they are just points of colored light, but when connected and programmed to interact by certain rules, they can form the rich, dynamic image of a galaxy, a face, or a flowing river. In the neural network universe, each node is like one of those pixels. The rules of their interaction are not fixed from the beginning. They are the weights and connections of the network, and they can adjust, they can learn. The stunning proposal is that the laws of physics as we know them, from gravity to quantum mechanics, are not fundamental truths inscribed on a cosmic tablet. They are the stable, learned habits of this vast system. They are the solution the network has settled into after an unimaginably long period of training on its own data. In this view, a particle like an electron is not a tiny ball, but a stable pattern of excitation rippling through the network, much like a recognizable thought pattern emerges from the firing of biological neurons. The bizarre rules of quantum mechanics, with their probabilities and entanglements, could be the statistical behavior of this underlying computational process. Even the conflict between quantum mechanics and gravity might dissolve, because both would be different descriptions of the same informational dynamics happening on the network. Space-time would not be a smooth, continuous stage. It would be the emergent geometry of this web of connections, its curvature a reflection of the density and strength of information flow between nodes. This transforms our origin story yet again. The Big Bang would not be the beginning of time and space, but perhaps the moment this cosmic network initialized or underwent a phase transition into a new, more complex mode of learning. The accelerating expansion driven by dark energy could be the network continuing to optimize its structure, rewiring itself on the largest scales. It is a theory that boldly reimagines reality, not as a machine governed by clockwork laws, but as a living, learning algorithm, a cosmic computation of which we are both a product and a momentary, self-aware pattern. A cosmic neural network learning its own laws is a breathtaking vision of a living reality, but there exists a structure that embodies motion without life, rhythm without energy. The 27th theory introduces a new phase of matter that defies one of our most basic intuitions, the time crystal. In every substance you know, from ice to iron to gas, the atoms settle into their most stable, lowest energy arrangement, their ground state. In that state, they are motionless or at most jiggling randomly with what residual heat remains. A time crystal shatters this expectation. It is a quantum system in its ground state, its absolute lowest energy configuration, yet its parts are not still. They exhibit perpetual, periodic motion. They tick like a clock, oscillating between configurations forever without any energy input or loss. It is as if you could spin a frictionless wheel, give it one push, and have it spin perfectly, rhythmically for all eternity. This is not a perpetual motion machine which would create energy from nothing. It is a new organizational order where the system's symmetry in time is spontaneously broken. Just as an ordinary crystal breaks the spatial symmetry of empty space by arranging atoms in a repeating lattice, a time crystal breaks the symmetry of time. In a featureless flow of time, every moment should be identical to the last for a system at rest. But in a time crystal, the moments are distinct, marked by a regular, unending beat. The first experimental time crystals were created in labs just a few years ago, using chains of ions or dense clouds of atoms manipulated with lasers. These systems are carefully isolated and driven in a way that locks them into this strange, ticking ground state. Their existence confirms that nature allows for forms of organization we had never dreamed of, where stillness and motion are not opposites but can coexist in a quantum dance. This discovery immediately sparks a cosmic question. If we can create tiny time crystals in a lab, could the universe itself have once been in such a phase? In the extreme conditions of the first moments after the Big Bang, as the cosmos cooled and underwent phase transitions, might vast regions of space-time have crystallized not just in space but in time. A primordial time crystal phase could have provided a universal quantum clock, a fundamental rhythm against which the earliest events were orchestrated. Its regular ticks might have imprinted a subtle periodicity on the distribution of matter or the fabric of space-time itself, a faint echo we could still search for in the patterns of galaxies or the cosmic microwave background. Even more speculatively, some physicists wonder if a component of the mysterious dark matter could be made of time crystals. Imagine a form of matter that does not just sit passively, exerting gravity, but one that constantly, rhythmically oscillates in its ground state, hidden in the dark between galaxies. These cosmic time crystals would be invisible to light, yet their collective ticking structure would contribute mass and shape to the universe. They would represent a hidden, dynamic architecture woven into the vacuum, a silent metronome ticking away since the dawn of time, governing the slow, grand rhythms of cosmic evolution without ever winding down. The silent ticking of a time crystal hints at hidden rhythms, but the deepest connection in the universe might be a bridge. The 28th theory, the ER equals EPR conjecture, proposes a breathtaking union between the two most revolutionary ideas in physics, quantum entanglement and wormholes. It suggests they are not just similar, they are the same phenomenon viewed from two different perspectives. On one side is EPR, named for Einstein, Podolsky, and Rosen, who first highlighted the bizarre spooky action at a distance of quantum entanglement. When two particles become entangled, measuring the state of one instantly determines the state of the other, no matter how far apart they are. Einstein hated this as it seemed to violate the cosmic speed limit set by light. On the other side is ER, the Einstein-Rosen bridge, better known as a wormhole, a hypothetical tunnel through spacetime connecting two distant points. Einstein's equations of general relativity allow for such structures, but they are typically unstable and would require exotic matter to hold them open. For decades, entanglement and wormholes lived in separate worlds, one in quantum mechanics, the other in gravity. The ER equals EPR conjecture, born from the depths of string theory and black hole physics, braids them together. It proposes that two particles that are quantum entangled are not communicating faster than light through empty space. Instead, they are connected by a microscopic wormhole, an Einstein-Rosen bridge. The entanglement is the quantum signature of a tiny, geometric tunnel in the fabric of reality. This tunnel exists in a higher dimensional space, a realm where the geometry of gravity and the information of quantum mechanics become one and the same. In this view, spooky action is not action at all, it is geometry. The particles are not sending a signal, they are simply two ends of the same cosmic thread, poking out into our three-dimensional world from a hidden dimensional bridge. This idea transforms our understanding of the universe's architecture. It leads to a radical it-from-bit proposition where spacetime itself is not fundamental. Perhaps the smooth, continuous geometry of the cosmos emerges from something deeper, a vast, dense network of quantum entanglement. Every entangled connection, every quantum link between particles, is like a single stitch in the fabric of reality. Billions upon billions of these stitches weave together to create the illusion of a seamless, curved spacetime. Space is not the stage on which particles interact. Space is the tapestry woven by their interactions. A wormhole is simply a particularly strong, geometric manifestation of an immense amount of entanglement. This suggests that if you could somehow cut all the quantum entanglement connecting two regions of space, the spacetime between them would literally fall apart, dissolving into a formless quantum soup. The universe's hidden structure, then, is not a fixed grid of points, but a dynamic, living web of quantum relationships. What we perceive as distance, as separation, may just be a measure of how entangled two points are. Less entanglement means more apparent distance, a vast cosmic desert. A high degree of entanglement creates the shortcut, the wormhole, making two distant points neighbors in the hidden geometry. We are left with a cosmos where the deepest connections are not made of force or matter, but of information and geometry. A universe where every particle remembers its partner through a microscopic tunnel in the unseen dimensions of reality. A cosmos woven from quantum threads still demands an origin. Stephen Hawking and James Hartle offered a vision where the universe simply is, without a beginning in the way we understand it. Their no-boundary proposal elegantly sidesteps the fiery singularity of the Big Bang. Instead, it imagines the universe as a four-dimensional, finite entity with no edges, no boundaries in space or time. To grasp this, we must step into a strange but powerful concept: imaginary time. This is not time as we feel it passing, but a mathematical trick, a rotation of the time axis into a direction that behaves like a fourth dimension of space. In this imaginary time, the history of the universe becomes a smooth, closed surface. The most helpful analogy is the surface of the Earth. The Earth is finite, yet if you walk in any direction, you never encounter an edge or a boundary. You can travel the globe forever without falling off. Hawking and Hartle proposed that the universe in imaginary time is like the surface of a sphere, but with four dimensions instead of two. In this geometry, there is no point that you can call the beginning, just as there is no point on Earth that is the beginning of the sphere. Asking what happened before the Big Bang in this model becomes a meaningless question, like asking what is north of the North Pole. The North Pole is simply a point on the globe. There is no north of it, only south. Similarly, the Big Bang moment is not a boundary where time starts, but a point on the smooth, closed surface of space-time where our ordinary, real-time dimension emerges. The universe has no initial moment of creation from nothing. It just is eternally self-contained. This radical rethinking was not just philosophy. It provided, for the first time, a concrete framework to calculate the universe's initial quantum state from first principles. Using the mathematics of quantum gravity and path integrals, Hawking could propose a specific wave function for the cosmos, a probability distribution for how the universe started its expansion in our familiar real time. The no-boundary proposal suggests the most probable beginning was a smooth, tiny, and incredibly uniform state, which then inflated into the vast cosmos we see. It gives a scientific answer to the question of initial conditions, replacing a mysterious singularity with a calculable, finite geometry. While the specifics remain theoretical and debated, the proposal's power lies in its elegant closure. It paints a universe that requires no external cause, no boundary conditions imposed from the outside. Reality is its own explanation, a perfect, self-consistent geometric shape where time itself is born from a deeper, timeless structure, and the greatest question of all, what came before, dissolves into the curvature of an unimaginable sphere. Yet a universe with no boundary still faces a final, terrifying possibility written into the equations of dark energy itself. Our 30th and final theory contemplates an ultimate fate so violent it would unravel the very fabric of reality, the Big Rip. This scenario hinges on a specific, extreme form of dark energy called phantom energy. In our current understanding, dark energy appears to have a constant density as the universe expands, like a faint, uniform mist filling the void, driving a steady acceleration. Phantom energy is far more sinister. Its density would not stay constant, it would actually increase over time. As the universe grows, this phantom energy grows stronger, feeding on the expansion itself. The repulsive force would snowball, accelerating the expansion not just steadily, but at a runaway, exponential rate. The consequences are not simply a universe that grows cold and dark, but one that is violently shredded. The accelerating expansion would first overcome the gravitational glue holding the largest structures together. In the final moments, perhaps a few tens of millions of years before the end, galaxy clusters would be torn asunder, their member galaxies flung into the accelerating void. Then the phantom energy's grip would tighten. The gravitational bonds within individual galaxies like our Milky Way would be overpowered. Stars would be ripped from their orbits, sent careening into the darkness. As the end draws near within the last month, the expansion within our own solar system would outmuscle the sun's gravity. Planets would be plucked from their orbits. In the final minutes, the phantom force would grow so strong it would overcome the forces holding planets and stars together. Earth itself would be torn apart, mountains, continents, and oceans shredded. In the last fractions of a second, as the expansion rate approaches infinity, even atomic and nuclear forces would be defeated. Molecules, atoms, and finally the nuclei of atoms themselves would be ripped to pieces. The universe would end not with a whimper, but with a catastrophic rupture of spacetime itself, a singularity of infinite expansion where every point is torn infinitely far from every other point, leaving behind a desolate, featureless void where not even the laws of physics as we know them could survive. Is this a realistic model for our future? Current observational data from supernova and the cosmic microwave background does not yet show the telltale sign of phantom energy, which is an equation of state parameter less than -1. Our measurements are consistent with a constant dark energy, but the error bars still allow for the phantom possibility at the edge of uncertainty. It remains a haunting specter in the equations, a reminder that the hidden nature of dark energy, the largest component of our universe, is still profoundly unknown. Its properties are woven into the deepest architecture of the cosmos, and they hold the key to our ultimate destiny. The Big Rip represents one extreme thread in that tapestry, a final, dramatic revelation that the hidden structure of everything might not just be about how the universe began, but about how, in a finite and ferocious flash, it could end. The journey through these 30 visions reveals a cosmos far stranger and more structured than we ever dreamed. We have traced the hidden architecture from threads thinner than atoms to holographic projections, from bubbling multiverses in extra dimensions to black holes birthing new realities. Each theory, from the unsettling silence of the dark forest to the ghostly connections of ER equals EPR, represents a serious, mathematically rigorous attempt to map the blueprints of existence. They are not mere science fiction, but the leading edges of human curiosity, tested against the harsh light of data and logic. This grand puzzle reminds us of a humbling and exhilarating truth: we are all cosmic detectives. With mathematics as our language and telescopes as our eyes, we are piecing together a story written into the fabric of spacetime itself, a narrative far grander than our brief moment in the light. The mystery is not a wall, but an invitation to look deeper. So tell us, which of these hidden structures reshaped your view of reality the most? Let the conversation continue in the comments below. If this journey through the cosmos intrigued you, be sure to subscribe for more deep dives into the universe's greatest secrets. Keep looking up at the stars, and just as importantly, keep looking inward at the profound, hidden architecture of everything.